My name is Sandi Metz, and I'm here today to talk to you about object-oriented design. Before we can have a talk, we need to agree about what that word means. What do you think of when you think of design? This? What do you think the bird asked for? We've all done this, right? I've done it. I know you have. I know you have apps just like this at home. So let me ask, we're smart people. How does this happen? How do we write complicated code where design leads us here, where it can be accused of making things worse instead of making things better? I want to start over. Let's agree about what design, let's first agree about what design is not. It's not what the ivory-towered architect told you to do. It's not those pictures that the committee gave you. And it's not even what you thought you were going to do to begin with. Design is simply the code. It's just the code. It's what you have left when you're done. More specifically, it's the art of arranging code. The fundamental target of design is the tension between the known needs of today and the changes that will arrive in the future. Code needs to work today just once, and it needs to be easy to change forever. I'm just going to repeat that. It needs to work today just one time. But your code is going to have to be easy to change forever. And it's at this point of tension where design matters. And its purpose, its entire reason for being, is to reduce the cost of change. If what you're doing or what you've seen done serves any other purpose, it might be well-intentioned, but it's not design. The design that I'm talking about is your friend, and it'll make your life and your code better. It's practical. And if it's to be of use, it's got to lower costs. So with this thought in mind, let's think of the kinds of things that we historically think about as design. Some things are like prescriptions, like patterns are prescriptions. If you have the problem that a pattern solves, it's a near-perfect solution. It works, and you can communicate with others. All you have to know is exactly what they do and exactly when to use them. Other things that we call design are bigger things like solid, like single responsibility, open close list, law of Demeter. These things are like famous, right? They have storied histories. Some are the result of well-known research. Somebody just seemed to have made up. But regardless, we agree that they're good and that we should do them, and yet somehow they don't keep us out of trouble. Sometimes the way we talk about design, it seems like people are just describing it, like Steve Freeman and Nat Price say these four things, and I love these words: loosely coupled, highly cohesive, easily composable, context independent. They're exactly right. If you knew exactly what they meant and how to achieve them, your apps would be perfect. So the question is, how do you get there, right? How do you bridge the gap between what happens when you put your hands on the keyboard and type and having your apps turn out this way? None of these things seem to be enough. I think we need diagnostics. We need simple ways to judge the goodness of code. And I'm going to suggest 4. These things are an inversion of Bob Martin's list of ailments, his rigid, fragile, immobile, viscous. But instead of describing bad code like his stuff does, these things describe good code. These are qualities that code should have. Code should be transparent. You ought to be able to look at your code and tell what's going to happen if you change something. You shouldn't find yourself in a situation 2 weeks later where you find that your test coverage wasn't good enough and something breaks in production, right? I didn't know it was related. I didn't know it was going to happen. You ought to be able to look at the code and tell what's going to change. Code should be reasonable. The cost of making any change should be proportional to its value. If your customer asks for a little change, it ought to take just a little change in code. If they ask for a big change, maybe you have to change some more code to do it. You shouldn't be in a situation where you tell your customers, I know that seems simple to you, but it wasn't written to do that. And so I can't make that change for you, right? You've never said that, right? We've all said that, right? It wasn't meant to do that. Sorry, I know it seems simple, but I can't help you. Third, your code should be usable. If you wrote it, you can use it. You don't have to copy it, you don't have to duplicate it, you don't have to hack around with it. It's if you wrote the code, you can use it in an unexpected context. And finally, code should be exemplary. More like it should be good. If you, your future forgetful self, the new intern, the new hire, the guy who doesn't know the domain, the bad programmer in your office, comes to your code and makes a change, the simplest thing for them to do ought to be something that's good for your code base. You shouldn't be in a situation where you're saying, well, I could hack it in and have it done by tomorrow, or I could do the right thing and it would take a week, right? The natural way that people are going to want to behave ought to be a thing that's good for your app. So together, these 4 diagnostics, they don't really tell you how to write code as much as they tell you when to stop. Knowing when to stop is important because design is never perfect, and you don't know everything. Your code will never be done. You just have to find a good place to quit. And so if your code is transparent, usable, reasonable, and exemplary, it's good enough. You're done. And so this set of diagnostics lets you write code to meet today's requirement, but that can still tolerate change. It lets you use design not to choose between options, but to preserve them. And if you think of design this way, it's easy to do. You can just do less. Okay, that was the intro. Now we're going to start looking at code. I know you can't see. So you can go there. All the slides are up there, and you've only seen like 10 slides, so you can get here pretty quick. Probably would be best if everybody didn't go there, like if you're sitting next to somebody. And I was assured yesterday by a Heroku engineer that this would guarantee a crash at Heroku. So share if you will, all right? Also, you can look ahead if you want, you're grown-ups, but you'll ruin the punchlines of all the jokes if you do. So stay with me if you can. So the rest of the talk's in 3 parts. The first 2 are concrete. We're going to have code examples. Each part has 3 examples in it, so we're going to have 6 examples altogether. It takes about 25 minutes. The first part's a little bit longer than the second part. Part 3 is tiny, and it comes at the end. Everything stands alone, and so if you get a little distracted and you need to read your email, just come on back. You'll be able to catch up. So, part 1, don't be a know-it-all. This is the app. We're a bicycle touring company. This is a company that arranges and leads groups of people on biking trips. Trips have bikes. Mechanics prepare bikes to go on trips. Trips ready to go. Bikes must be prepared. The code's already written. Trip has a prepare method. And in example number 1, that prepare method, Trip tells mechanic how to behave. Here's the code. Okay, don't hate me, it's UML. Who has drawn a diagram like this? Drawn yourself personally. Who has seen one? Okay, so this is a sequence diagram, and it shows the messages passing between objects. They are good, right? It lets the cruft of the implementation details of the code fall away, and it lets you concentrate on the objects and the messages. The boxes represent classes. They repeat at the top and the bottom. There's a vertical line to connect those boxes just so you can tell what is related there to mechanic. When a message is sent, you see this horizontal line. It's got the name of the message above it. There's an arrow, a solid filled-in arrow on the side on the vertical line of the receiver. That gray bar says that mechanic is busy processing this message, and the dashed line is the result being returned to the caller. The whole thing gets started because someone sends prepare to trip. Now, if this was real UML, there would be another box over there where someone sent prepare. But I am confident that the UML police are not going to come and get me for just making my best use of these diagrams. So use them, draw them on the whiteboard, erase them, be done with them. So this is a simple diagram. This diagram represents Trip's implementation of prepare. And it's a simple method, but as you can see, Trip sends a whole bunch of messages to mechanic. It knows a lot of things about mechanic, and I want to give the things it knows names. So I'm going to put these gray bars up on the side. We'll call them knowledge bars. In them, you can see that Trip knows what Trip does, mechanic knows what mechanic does. They also each know how they do it. What they do is their public interface. How they do it is hidden. It should be in their private interface. What they do is stable. How they do it is unstable. The pairs of green boxes then mean things that these classes, these objects should know about themselves. However, there's more. Trip knows things about mechanic. I contend that Trip knows mechanic exists, but you may not agree with me, and I'm going to ask you just to hold on to that thought. We'll get back to it. However, Trip certainly knows what mechanic does, but unfortunately, it also knows how mechanic does it. And it's this how message that's risky. It adds vulnerability. If mechanics add a step in bike prep, like checking the cables, all of a sudden Trip has to change. Even though it doesn't really care about that, it just wants bikes to be prepared. How can you tell that these are how messages? One of the easy ways to tell is that there are 4 of them, right? There's probably something that they're all trying to do. But the other thing, even if there was only one, you can always ask yourself, like you want to send a message rather than implement behavior. So you can ask yourself, am I the last guy that could possibly know this? If I'm the last guy, then I do it, right? But this clean bicycle message, knowing that clean bicycle is part of bike prep, could happen in mechanic. And if it could, it should. And it should happen there and only there. And so in this example, Trip knows too much about mechanic. The app works fine for today's requirement, but the way the code is arranged, tomorrow's change is costly. Trip knows internal implementation details about things that are mechanic's responsibility. And how do you know that you shouldn't stop? How do you know that you should rearrange this code? You can measure it against true. You can ask yourself, is it transparent? Well, yeah, sure it's transparent. You can tell exactly what will happen if mechanic changes, and it's not good. There are many ways in which mechanic could change that would force a change to Trip. Is this code usable? Well, not really. You can only get a bike prepped if you have a Trip. You either have to duplicate that code, like you can't just talk to mechanic and give them a bike and have it get prepped. And it's clear that more code like this would not be good, right? It just gets worse if you duplicate this code in other parts of your app. So let's fix this. Let's make Trip know less about mechanic. And we'll do that in example 2 by having Trip tell mechanic what to do. Here's the sequence diagram. Now we're sending just one message. We've wrapped those 4 how messages up in a single what message. And that what message is in the public interface of mechanic. It now implements prepare bicycle. Last we saw the knowledge bars, they look like this when Trip was telling mechanic how to behave. It was sending messages that should have been hidden behind mechanic's public interface. It was duplicating knowledge that should only have existed in mechanic. But now that mechanic implements prepare bike, it hides those unstable private things behind a stable public interface that describe what it does, and Trip can send this new message and collaborate with mechanic without knowing how it behaves. This change improves the code. The multiple dependencies that it used to have been reduced to this one. Trip knows fewer things that might force it to change. And the total set of things that Trip knows decreases. It's more stable because it knows less. And this was an improvement in the code. But most of you probably already kind of get this idea, right? When you first came to OOP from procedural languages, you probably did a lot of this where you like put a bunch of methods over there and then you have some guy over here send them all. And then that spreads out through your entire code base and something changes and it just like, there's this wreckage where you have to change a lot of things. So the code itself, writing object-oriented code probably taught you something about this, that you want to shove that behavior back into the class that should own it and construct stable public interfaces. We write a lot of code just like this, and many times it is perfectly appropriate and you should stop here. Many times it's right. However, Trip still knows things about mechanic. So I will stipulate to these facts. Objects exist, they must collaborate, they do so by sending messages, and somebody somewhere has to know something in order to get anything done, right? I agree that there's gonna be a connection between objects here. However, knowledge is dangerous, and it's important to understand, to be clear about what you've let objects know, and to explicitly decide if they should know it. If we apply true here and ask if it's transparent, well, sure, it still is, right? And is it reasonable? Well, it's way more reasonable. Most changes to mechanic don't affect Trip, just that one method in its public interface, which should be pretty stable. Is it usable? This is way better, right? You can now get a bike prepped if you have a mechanic. Is it exemplary? That's a big question. Would more code like this be good for your app? And in order to answer that question, I'm going to ask another one. Who got better? Mechanic, right? Mechanic's way better. Mechanic, has a better public interface. There's less chance of changes made in a mechanic cascading into other objects. Mechanic doesn't itself depend on anything. Mechanic, in our example, is upstream from all the other objects. What about trip? Well, trip got better, right? Trip has fewer dependencies, but it still knows things about mechanic. It knows the prepare bicycle method, and this is a dependency. And when things that you depend on change, you might be forced to change. Managing dependencies is at the center of design. Everyone matters, and you don't want to acquire them blindly or by accident. You have to manage them because they will manage you. If you don't choose your dependencies, you can end up in a situation where they all run the wrong way and every change cascades through your app and it makes your life a living hell, okay? So this is a piece of knowledge that you should explicitly decide. Here's the rule. You know this rule, right? Depend on things that are more stable than you. It's simple enough. Depend on things that change less than you do. And in our case, we have a dependency. Example 2 has evolved to where trip depends on a message in the public interface of mechanic. It depends on prepare bicycle. Dependency direction is a choice, and whether or not you noticed it, you just made one. We're trying to answer the question, is this code exemplary? Would more like it be good? And in order to answer that question, we have to know which of these two objects is more stable. If mechanic as a whole is unstable, its public interface is at risk. Changes in mechanic might end up forcing changes in trip just because of the code is arranged, just because of the direction of this dependency. So to write exemplary code, you have to know about the relative stability of the objects involved. And the cold hard truth for new applications, you don't know. Early in design, you don't know which of the objects are going to turn out to be more stable. Sometimes this isn't a big deal, but unfortunately, the objects about which you are most uncertain are probably the most important ones. They're at the center of your design. They're the thing that makes you special. They're the thing that gives you a competitive advantage. You may not know what business you're in until you write this app and people start using it. The objects you end up caring most about are often the ones you currently know the least about. And so if that wasn't already bad enough, if not knowing isn't bad enough, you can't know. You can't figure it out. Only time will tell. So now you're in this situation. Two objects need to collaborate. You're going to have a dependency. The dependencies will kill you if you get them wrong, and there is no way to know what's right. Sucks to be you. Okay, this is always true. This is design's fundamental condition. You cannot see well enough to predict the future. And design, frankly, is okay with it. As a matter of fact, design can help. It offers a solution. Design says use uncertainty. It's telling you something. There's a piece of information here at a time when information is in short supply. It identifies unstable places at the center of your domain that represent the core of your business and are likely to change. It identifies where you are most at risk. Things will change. You can't know how. This is not the time to make a wild guess and implement one of the future alternatives. It's time to write code that can tolerate change. So here's the rule. If two objects must collaborate and you don't know which is more stable, you have to make them know as little about each other as possible. Uncertainty is not a license to guess. It's a directive to decouple. And so here's how we decouple trip from mechanic. We can have trip tell mechanic what trip wants. Here's the sequence diagram. Instead of sending prepare bicycle, we send prepare trip and pass self along as an argument. Mechanic immediately calls back and gets the bicycles. Now, mechanic's implementation of prepare trip assumes that whatever argument got passed can provide bicycles. This is a new dependency. I just created a new dependency. But mechanic's expectation that the argument here can provide bicycles is very stable. Mechanics are about bicycles. If you want to deal with a mechanic, you ought to be able to provide bicycles. Now notice the input argument doesn't need to be a trip. It just needs to be someone who can respond to bicycles. It can be any kind of object. Just has to answer to that interface. Mechanic actually implements prepare trip by sending prepare bicycle to itself. This is a perfectly reasonable method. It's part of mechanic's public interface. And there may be other objects with whom it collaborates for which it is appropriate for them to have a conversation at that level. Last we saw the knowledge bars, things look like this. And this change, where we have trip tell mechanic what trip wants, it removes knowledge from trip of what mechanic does. And the overall knowledge in trip has been reduced again, and trip now knows even less. This change drives these objects further apart. They're more independent, and changes to one are less likely to cascade over into the other. I know that's still bothering you. I promise we'll get back to it. So what just happened? We traded a possibly fragile dependency, a dependency about whose direction we were uncertain, for more stable ones. Trip used to depend on prepare bicycle, and now trip depends on prepare trip, a very trip-like thing. And mechanic depends on bicycles, a very mechanic-like thing. These two objects are less entangled, their dependencies have been weakened, and their coupling is loosened, and because of that, changes to either are less likely to cascade into the other. Pushing these things apart made the app more stable. So that's the end of part one. We're gonna have a little recap. Example one, right? Trip told mechanic how to behave. We swapped that for a what? It got better, the code got better, and then we traded it for having trip tell mechanic what trip wanted instead of sending a message in mechanic's public interface. Notice that we would have stopped at step 2 had we known that dependency was running in the right direction. At step 2, if we knew that the dependency was wrong, we would have just reversed it, right? We didn't do this because the dependency was wrong. We did it because we didn't know, and we didn't want to make a choice. We wanted to loosen the coupling between those objects, so when the change came that we did not know what the change was, it would be this code would be more flexible. So you don't have to guess what the change is going to be. You just need to know what's going to change. Design doesn't make you bet on the outcome. Just notice uncertainty and create objects that respect it. You can do design to preserve your right to do design later. So knowledge creates dependencies. They're risky. Uncertainty will tell you where to loosen coupling, and that's going to lower your cost. This is what design is. And that's the end of part one. Okay, so you're still here, right? So can everybody see the slides, right? You have some access to them. Okay. So the next part, part two, it's a lot like part one. I'm going to take 3 examples, work them through a couple of refactorings. Part two is entitled, It's Ducks All the Way Down. So it's the same trip and mechanic objects that you've already seen. The first example, example 4, starts off with trip telling mechanic what to do. Here's the sequence diagram. Trip is sending prepare bicycles and passing an array of bicycles. If this example seems familiar, it just means you're keeping up because it's a lot like example 2. Right? This is the what message. We stopped here because that was the correct dependency. We believed that we had the dependency running in the correct direction between those 2 objects. Let's take a closer look at trip's actual implementation of prepare. Look, code. Trip has 3 attributes, bicycles, customers, vehicle. Here's its implementation of prepare. It takes a single mechanic as an argument. It sends that guy the prepare bicycles message and passes the array of bicycles. This code works for today. But let's change something. Let's imagine that trip preparation changes. And now when a trip gets prepared, things need to happen that involve not only mechanics, but also trip coordinators and drivers. Those classes already exist. The trip coordinators buy food, and the drivers take care of the vehicles. So your task is to change the prepare method so that all the correct preparation gets done and includes these new classes. And the question is, how will you do it? And the answer is, it depends. It depends. And now I'm finally getting back to that point about whether trip knows about the existence of the mechanic class. We all know that trip doesn't know. Ruby is dynamically typed. This argument is name mechanic, but it could be any kind of thing. However, it's not trip I'm worried about, it's you. I fear that you, in your heart of hearts, think of this argument as being an instance of mechanic. I fear that you're attached to this. You expect to receive a mechanic. You picked the prepare bicycles message because it was in mechanic's public interface. You're doing an implicit check of this argument's class. And if your imagination is constrained by an expectation about the class of that argument, when you're asked to include trip coordinators and drivers in trip preparation, you're forced into a corner where you have to check the class of an object to know what message to send it. Example 5, you have to write code that looks like this. If you're sending prepare bicycles because you expect the mechanic, and you start getting instances of other classes on your argument list, you have to check the class of each to know what message to send. Your formally implicit check becomes explicit, and it now becomes obvious that all along you were saying, I know who you are, and because of that, I know what you do. A bomb just went off, right? This code knows a bunch of classes and messages by name. Any new trip preparation requires a change here. Changes in distant places unexpectedly break things here. Think of the setup. How will you test this? This is the first step on the path to application self-destruction. Don't confuse this with framework code that you see where really nice people let you pass a bunch of different kinds of input arguments, and they say case string, case hash, case array, right? They're just being friendly. Those are Ruby base classes. They are stable. Array is going to behave the same way tomorrow that it does, today. String is not going to change, right? Hash is what hash is. Those, even though there probably is a way to do a different thing there, it's not really necessary because those classes aren't going to change. Your classes are. You are like so dead meat here if you do this. So let's evaluate it against true, right? Whew. So let's have a look at the sequence diagram. Like, oh no. It's just bad all the way around, right? The code is too complicated. And the roots of its complication lie in its concreteness. It's complicated because there are too many different concrete things. There are a bunch of specific classes and a bunch of specific messages, and Trip has to know all of these specific things in order to get prepared. This knowledge is a burden to Trip. It creates dependencies that make Trip costly to change. What Trip actually wants is something far simpler. And finding that simpler thing means identifying the underlying abstraction. Forget about the classes of the arriving arguments and ask yourself, what does Trip want? From Trip's point of view, it just wants to be prepared. So how can we decouple Trip from all these dependencies and still get it prepared? You can just have Trip expect preparers and tell them what it wants. Example 6, here's the sequence diagram. Mechanic, trip coordinator, and driver are gone. They've been replaced by this preparer. Trip sends prepare Trip to the preparer, and it passes self along as an argument. The preparers call back, get whatever details they need. Do you recognize this? Yeah, it's example 3. Right? Except instead of sending that message to a mechanic, we're sending it to a preparer. So what is a preparer? It's just an agreement. It's an agreement about the public interface of an idea. It's just a bargain that these objects have with one another. It's a duck type. So here's the code that implements it. Instead of receiving a single mechanic argument, we get this, we just change the name, right? It's an array, so we call it preparers. Send prepare to iterate over the array, send prepare Trip to each pass in self. Each class that behaves like a preparer implements prepare Trip. It takes this argument, I call the argument Trip. I don't care what it is, it's a Trip-like thing. It honors this interface. The interface it honors is this one, right? Everything they need, everybody agrees that it's all gonna work. Mechanic, trip coordinator, and driver are preparers, and the preparer duck type is an abstraction. It sorts through the concrete complexity of all those classes and messages and gets to the heart of the question of what Trip wants. Trip wants to be prepared, and it's this desire for preparation that's stable. And because it's stable, you can rely on it. You can trade the unpredictability of what others do for the constancy of what you want. Making this trade loosens the coupling between these objects and reduces the cost of change. We share no code There's no module. It's just the idea. It's the signature of that method, but it doesn't matter. It's a duck type. And it's your expectation about an object's type that lets you imagine how it will behave. Trip expects preparers, not mechanics and trip coordinators and drivers. And preparers expect that whoever called them can give them what it needs. And so this whole bargain operates on faith, on trust. Trip has to trust the preparers. This whole malleable structure gets destroyed if Trip gets scared and starts checking class. Preparers have to be trustworthy. Their trustworthiness is what allows Trip to trust them. They can never do anything unexpected which would force Trip to check their class. They have to behave like preparers. They have to honor this public interface. Trustworthy objects understand more about themselves and what they want, and they know less about others and what they do. They act responsibly. If everyone behaves, everything works. An application constructed of loosely coupled trusting and trustworthy objects is infinitely changeable. And achieving it requires that you depend less on concretions and more on abstractions. It requires that you think about objects from the inside, from the message sender's point of view. It requires designing objects as if they live in isolation, in a bubble where they don't and can't know what other classes exist. Every sent message blithely expects that the receiver is just going to do the right thing. It doesn't micromanage, it operates on faith. And there are no half measures. You can't hedge. You have to go all in. There's no place in here. One check on type, one check on class will bring this whole structure to its knees. So design says think more about the message and less about the class. You can follow the message and find stable abstractions. And when you depend on those abstractions, you can write code that you'll get to keep. This is design. Whew. Okay, so that's the end of part 2. You're still all here. That's good. So here's the reprise. You saw this already, right? This is part 1. Example 4 started off where example 2 was, right? We stopped at that point. 5, because we were stuck on mechanic, when we had to add new classes into the mix, we had to check class to figure out what message to send them. And so things got dramatically worse when we put that case statement in there to check on class. But it turns out the solution, the way to solve that problem was to basically use the same solution as example 3, where we sent messages, the prepared trip message to it, except we thought of it as a preparer instead of a mechanic. The thing that reduced the risk in the face of uncertainty was the stable abstraction. They're the same, right? There's 2 different apparent problems that you would describe in 2 different ways, but the solution to each is the same. There's an underlying abstraction where objects know more about themselves and less about others. Okay, so I've been up here for 33 minutes, and I've been talking about this idea, coupling. And it's a useful idea. It's a big idea. Like, understanding this would make your life better, right? No doubt about it. If you can get this concept, everything gets easier in your code. But however, in some ways, the stuff I'm talking about is the same as that stuff I talked about at the very front. It's just a few more techniques, right, of one of the many million. And because it is like there's this big pile of concretions, right? There's thousands of techniques, and if you could just learn them all and know where to apply them, your code would get better. However, that complexity suggests that there's simplicity here. Like, these 2 ideas are part of some bigger idea, and if we could just find the abstraction, we could use it to guide our behavior in the future. That brings us to part 3. It's hard to describe what we do, and we try to talk about these things. Putting words on the concepts is necessary because we have to try to communicate, but doing so removes us from what's really going on. Programming is an art. Good designers are artists. They know these techniques, but techniques are not what lets them create. They have a feel for what's right, and it's this feeling that guides them. Design is not about words. It comes from that part of you that wakes you up at 2 in the morning with a solution. That part that waits patiently all day while you struggle and then tells you the answer on your walk to the subway. You can memorize all these techniques and that kind of works, but everything is easier if you acquire a feeling for design. If you have it, you'll hate what feels bad, and you'll fuss with that feeling until it goes away. And it's in that fussing where you learn these techniques for yourself. If I could give you a feeling about design, it would not be about what goes in every object. It would be about the space between them. When there's not enough space between objects, they're entangled, and you can't get at them. You can see glimpses of possibilities, but it's just frustrating because you can't reach them. When objects have space around them, they have room to move. Possibilities open up that allow anyone to use them. When objects aren't entangled, someone can customize just one, or they can create an unexpected variant. Unencumbered objects can multiply and grow and change until they meet all manner of needs that you yourself might not even understand. If you set your objects free, others will give them new utility. They'll discover broader, unexpected uses. And these new uses will at first be recognizable, simple variants of the original. But when objects stand free, they can be changed, they can evolve, they can be combined into new forms, they can be arranged into new combinations, they can be morphed into shapes that are brilliantly unrecognizable. They can be used in ways that you could not have imagined for purposes that you would not have conceived. You can free your applications from the constraints of your own imagination if you just leave enough space between objects. Design is the thing that lets you put off design decisions until later. It reduces risk and lowers costs. It lets you do less. It lets you do this. All right, there you go. Thank you. So by my clock, I have 2.5 minutes for questions. If the mechanic realizes it needs to be paid, yes. Like paid to... Just do your quick thought process. So you're saying when it prepares bikes, there's going to be a callback to charge?
Somehow it has, right. Does it take money as another argument? Does it expect...
Oh, it's a callback. Oh, I would say that. No, it's a callback. Absolutely. Yeah. I mean, there's a public interface for getting money, right? There's a way that you charge. There's a way you do it. I mean, if you make it past the argument, you've coupled it. And it means you can't, preparing bikes somehow involves money. They probably shouldn't, right? It'll work just fine if you decouple it as much as possible, and then you can change it any way you want later. Wow. I thought I was just going to be stumped, and then I knew an answer. Yes, in the far back. The question was, have I written or blogged about it? I'm unfortunately writing a book that is coming at a glacial pace to a bookstore near you. It's called Practical Object-Oriented Design with Ruby. Oh God, you're going to make me say. It's halfway done. It should be done by like Christmas time, so it'll be available next year. See, I didn't pay him to ask that question. Other questions? I love talking about design. Oh, here we go. Sure. He asked me, when would you not want to pass self, right? Call a message that says what you want and pass yourself. Here's the deal. Everything is judged by what it costs to deal with change. And so you're trying not, you should never write a bit of code that's for a feature that you anticipate. Every bit of code that's in your app better be being used right now. This situation, by their nature, the 30-minute talk example is slow. Imagine that you're building a new business and there are 20 important objects at the center of your domain, and you're very uncertain about how they're all going to work out with each other. That's a place where you very likely will lower your costs if you proactively reduce coupling. If you have a sense, I mean, my criteria for how nervous I have to be about the direction of that dependency in order to break it like this, I have to be a little nervous. Like, if I'm a little certain, that's probably good enough to leave it, right? I mean, everything is good enough. Like, the design is about leaving yourself options, right? Preserving your right to choose later, not about choosing now. So every time you take a step, really the question I ask myself when I'm doing design is, what am I going to do when I find out I'm wrong? I don't think I'm right. I'm never right. Maybe you're right, but I'm never right, right? And so, like if you call a bunch of messages and pass self in a million places and that starts feeling costly, back up and look and say, well, are some of these more stable than I thought? Maybe I can back down on this. But this is a lot of help if you're gonna have serious dependencies later with a bunch of objects whose relationships that you're uncertain about. Like, if you could go away from this talk today recognizing that a loosening of coupling is a solution to the problem of uncertainty as opposed to choosing a coupling, because that's what you've done, right? If you don't loosen it, you chose it. And so preserve options when you can instead of making choices.
You have time.
I have time. Are there more questions? I'll be on the boat. So come talk to me later. Thank you again.